Time series are all around us. Things such as the daily stock prices, or even weather data. Say we looked at a plot of temperature over the past 100 years. All of these are sequences of data that are time dependent. Even our personal data, like daily body temperatures or blood pressure readings or glucose levels. Here's a time series plot of my daily waking body temperature. Now, this particular pattern occurs because of the shifting hormones in a woman's body. Estrogen is present at the beginning of a woman's menstrual cycle, causing her lower body temperatures to occur. And now at ovulation, a woman's body releases an egg. And that's when progesterone is the dominant hormone, and it actually causes a rise in the body temperature. Now you'll notice the temperature observations, they're not random. In fact, there's correlation from one value to the next value. And so time series analysis, it gives us a way to model this response data that's correlated with itself from one point in time to the next point in time. This is data that has a time dependence. Now, to analyze this type of data, we need a new method that can model that dependency on time. And now this is another new way of thinking, and it might remind you a little bit of spatial statistics. Now, previously, we've looked at modeling relationships of X's versus Y, so predictors versus the response, using lots of different ways: linear, polynomial, logistic, all of those types of regressions. But now here's what's different. Time is the independent predictor variable. And in fact, we have a single measure that we track from one population. And we want to understand how it is that that measurement is going to change over time. Time itself is now the measure. So our goal is to understand how our response measurement, Y, varies with respect to time. Now, formally, a time series is a collection of evenly spaced numerical observations that are measured successively in time. Three main goals of time series analysis. The first, we really want to describe the series. This is where we identify patterns or pull out any trends that we might see. Second is to explain it. How do we understand it, and what kind of models can we put on it? And then the third goal is forecasting. Can we predict short-term trends based on the patterns that we see in our time series? Now, as statisticians, we are especially interested in understanding the underlying structure so we can forecast future values. And so our goal is to develop a statistical model that describes and explains the data in such a way that we can forecast with precision. All right. We begin by looking for underlying structure in the data. The most common patterns that we'll see are trends, which can be linear, they can be quadratic, even exponential. So in R, we set the trend of a model by using the LM command. We've done this before. Let's do an example. Here's the data file wages, and it contains monthly values of the average hourly wages in dollars for workers in the US. And these workers are from the apparel and the textile industry, and it ranges from July of 1981 through June of 1987. Now we're going to pull that data from the TSA library, and the data is again called wages. Let's look at a plot of it using the plot function. All right, here's a time series for the plot of this data. You'll notice there's a really nice increasing trend. I wish my salary looked like that over a 6-year span. So how might we model this as a time series? Well, if we didn't know it was a time series, we would probably fit a linear regression in the data, right? We'd look at that significant predictor, and then we'd check the residuals. Through normality, we'd check the QQ plot. So in fact, time series analysis follows much in the same way that we've already learned. We're going to fit a line to that data, but our predictor is now a function of time. All right, check the residuals. We're going to then see what's left over, and we hope that they look like noise, right? We don't want them to have any pattern at all. So let's fit time to the wages data. So here we're doing wages.lm, and we're going to fit a linear model where our y response variable is wages, and the predictor is the time associated with wages. So we use time, parentheses, wages. So that tells R that we want to do a time series model, even though we're using the lm command. Here's the output. So we fit our model. Check out that estimate. So you'll see the estimate for the time of wages, and it's super significant. That's the lowest the p-value can get. And we've got a nice R squared, 0.97. It doesn't get much better than that. So with a multiple R squared of 97% and a highly significant regression coefficient, the case is closed, right? Well, we still got to check those residuals. Don't forget about that. Let's check out our residuals. Whoa. So notice here, we've got a slight problem. In fact, those residuals don't look random at all, right? There's clearly a trend and a pattern in this residuals. They're not centered around 0, and they don't look random. They tend to hang together too closely. And so what that tells us is there's still more structure that we need to take out from the data. All right, so next, why don't we try a quadratic fit? Let's see if that fits our data any better. So here's our quadratic fit. So this is like fitting a polynomial regression, except here, remember, our variable is time. So now we're fitting wages as a function of the time of wages and then the time of wages squared. Check out our output. Again, all of those predictors are significant with extremely low p-values. And notice what our R squared value goes up to, close to 99%. So based on this regression summary, it appears like this ought to be the best model. I mean, R squared can't get much better than that. But let's check out the residuals. It almost feels frustrating that we had such an amazing model and our residuals still have some pattern in them. But we still want to check that. So it doesn't look so great, but how are we going to check those residuals exactly for normality? Well, one thing we can do is look at the histogram, right? We want our histogram to be normally distributed, so look roughly like a normal distribution. And actually, if you look at our residuals, they do, right? They're nicely in between 3 standard deviations of our mean of 0. But remember, we can't just eyeball a histogram. What else might we look at? The QQ plot, exactly. Here's a QQ plot of those residuals, and that looks like normality to me. But we're not going to stop there because we can't check normality with the naked eye. We always end up doing a Shapiro-Wilk test. Let's do a Shapiro-Wilk test on the residuals from our quadratic fit. All right, here's the results of our Shapiro-Wilk test. And notice, we have a p-value that is not significant. So it actually confirms that our residuals are normally distributed. Now, once again, we've now transitioned to a sequence of random variables. So y1, y2, y3, where now our y sub t is the value of y at time t, for t equals 1, t equals 2, and so on. So a natural question is this: what's the expected value? What's the variance? What's the covariance? And is there a correlation in this new context? Well, not much changes, except the notation. Let's see how these look in the time series context. Now, the mean function of y, we define that as m sub t. So this subscript t is telling us that now we've got a temporal dependency that affects that mean function. And this is just the expected value of our data, y sub t. We also have the autocovariance function. Now this is different from covariance, right? Covariance looked at how two different variables varied together. Autocovariance, right? That auto is saying I'm varying with myself, right? So this is the autocovariance of y sub t because it's telling us how the series y at time t varies with itself at time s. And so we use this notation called gamma. Gamma of t and s is the covariance of y sub t with itself at a point y sub s. So this is just the expected value of y sub t minus mt and y sub s minus ms. We also need the autocorrelation function for our series. Now again, we've talked about correlation. Autocorrelation tells me how correlated the series is with itself. And that's just defined as the autocovariance divided by the square root of the variance for each of our series. Now, if we've got autocorrelation values that are near plus or minus 1, that tells us that we've got a strong dependence between y sub t and y sub s. Or values near 0 tells you that there's really not much linear dependency in your data. And if you get an autocorrelation equal to 0, then that means your series is independent. So at no point am I correlated with any other value on the series. So we need a measure to define sort of randomness, the standard amount of randomness that we would expect in a series that had no temporal pattern. And we use the term stationarity. So a stationary time series is one that has a constant mean, it has a constant variance, and it has a constant covariance function. And the covariance function is independent of time. And so we often look for stationary time series because once we get to stationarity, it means we've taken everything else out of the model. We've already accounted for the trend and the seasonality, and what's left is just the noise. So whenever we see a series is stationary, or it looks like noise, we get excited. Now, non-stationary series, on the other hand, are processes that have trend in them or seasonality. And we can't forecast them directly. We have to transform them in some way to model that seasonality or model that trend so that we can then do the forecast. Now, in general, time series are going to attain trends, seasonality, and serial dependence. Trends are just consistent directional movement in the series. They're either going to be deterministic or stochastic. When we say stochastic, we just mean sort of random movement. Now, a deterministic trend allows us to provide an underlying rationale, while a stochastic trend is a random feature of a series that will probably be unlikely for us to explain. Now, we often see trends in financial series, particularly commodities, prices, and many commodity trading advisor funds. They use these sophisticated trend identification models in their trading algorithms. I wish I knew some of those because I might do some time series trading myself. Secondly, we've got seasonal variation. Now, many of the time series contain a seasonal pattern, and this is particularly true in series that represent business sales or even climate levels. Now, in quantitative finance, we often use seasonal variation in our commodities, particularly those that are related to growing seasons or annual temperature variation, such as natural gas. Now, the basic objective, it usually is to determine a model that describes the pattern of the time series. All right, let's consider two types of models for patterns. First is the Autoregressive Model. That name says exactly what it does. Autoregressive. I'm going to regress onto myself. These are models that relate the present value of a series at some time t to its past values. And so we call that an ARP, so Autoregressive Model of order P, where P is basically the number of lags or the number of steps you're going to look into the past. Check out this model. Y sub t equals phi1, so that's the notation phi 1 times y sub t minus 1. So what that first variable says is, I'm going to take some weight, phi1, and I'm going to multiply it by the data value that's right behind me, plus phi2 y sub t minus 2. So again, I'm going to take another weight, phi2, multiply it by the series value that's 2 steps behind. And I do all of this out to order p. Now, let's simplify that and just look at the Ar1 model, for example. We could write it as follows. Y sub t is equal to phi1, y sub t minus 1 plus e sub t. Now, if your phi is a high value, like 0.9, what that says is my value at y sub t is equal to 90% of what I was one step back plus some noise. So your dependence on your previous point is a lot higher. Whereas let's say that phi were something like 0.1. Well, then you're not really getting as much information from your neighboring point. You're saying, hey, I'm only going to take about 10% of you, and then I'm going to do my own thing, add some error. So the assumptions of the Ar1 model are that the errors are independently distributed with a normal distribution that's centered at 0 and has a constant variance. And these errors are going to be independent of your time series y sub t. The second model that we're interested in is an MA model, a moving average, and it goes out to order Q. Now, these are models that relate the present value of a series to the past prediction errors. Check this out. Y sub t is equal to E sub t, so that's just an error term, plus theta 1 E sub t minus 1. So what am I doing here? I'm now taking the error term associated with my value yt at time t minus 1, and that's what I'm using in this model. And I'm weighing it by theta 1. Likewise, we add theta 2 E sub t minus 2. Same thing. Now I'm going 2 steps away, taking the error associated with that time at point t minus 1, multiplying it by theta 2, and adding it to my model. And I can do that out to order Q. Now, these past prediction errors have to be estimated by nonlinear methods, and they're known as moving average problems. Now, in the MAQ way of thinking, the observations of a random variable at time t are affected by the shock at time t minus 1. And they're also affected by the shock at an earlier time. So you can think of these E sub t's as random shocks that go into the model. So for example, let's say we observed a negative shock to the economy. Maybe it was a catastrophic earthquake. Then we would expect that this negative effect would affect the economy not only for the time it takes place, E sub t, but also in the near future. Right? So this kind of thinking is what motivates MA models. So together, we can take these time series models and combine them to get ARMA models. We call these autoregressive moving average models. Now, ARMA models provide one of the basic tools in time series modeling. And when we include things like differencing, so differencing is taking the difference, y sub t minus y sub t minus 1, we get an extended class of models which we call ARIMA. And now that differencing, which we'll look at in a second with an example, is the integrated part of the ARIMA. So autoregressive, integrated, for differencing, moving average model. So this is an extensive class of time series models. Now, ARIMA series, they often have an underlying linear trend, and they sometimes contain seasonality. Seasonality is a cyclical fluctuation that reoccurs seasonally, sometimes throughout a year or over a month or quarterly. Now, the other common pattern in a time series data set is that seasonality. And you could also think of it as a kind of periodicity. Right? A time series repeats itself after regular periods of time. So a less regular example of a season is the business cycle, which also plays an important role in economics. Now, a smallest time period for this repetitive phenomenon is called a seasonal period. And we often denote that with the letter S. Now, S here stands for season, and it's easy to confuse that S with the standard deviation, or the S squared of the variance that we often talk about. But in terms of time series, when you hear S, think S for season. So, S is the periodicity of a seasonal time series. So for instance, the series of monthly sales of a department store in the US tend to peak at December, because we're all buying gifts, and it tends to be periodic, with a period of S equals 12, so a 12-month season. Now, what if we have a quarterly pattern in ice cream sales? Well, in that case, we would have a seasonal pattern with S equal to 4. Now, a classic time series is the monthly airline passenger time series. This was first investigated in 1976 by George Box and Gwilym Jenkins, two pioneers of the time series methods. Let's check out that time series plot of the original series. All right, here you see the plot of airline passenger data. Notice they have a nice increasing trend, but also there's a seasonality component and the variance is increasing. So the variance is the spread of our data. Notice how that spread increases over time. That means our series is heteroscedastic. Remember that word? All right, one way that we can account for heteroscedasticity, or increasing variance, is to transform our data. Here, we take the log of the data. And notice what that does. Notice how we no longer see that increasing variance over time. Now, the graph of the logarithms displays a much more constant variation around the upward trend, right? Check out, also look at that change on the y-axis. In our original data, it ranged from 100 to 600. And now on the log transform data, it ranges only from 4.5 to 6.5. Right? So notice that log transformation has removed the increasing variability. Now, the first difference of a time series. This changes from one period to the next. So if y sub t denotes the value of the time series at point t, then the first difference is going to be the difference between y sub t and y sub t minus 1. And so we use differencing methods often because they help us to eliminate trends. In fact, if I have a linear trend in my data, when I take the first difference, so for each data point, subtract the one behind it, I eliminate my linear trend. It gets me closer to a stationary series. Likewise, if I were to take a second difference, it would eliminate a quadratic trend. Let's look at a difference process on the log of our series data. So here you see we've taken the first difference of the airline data. And notice, nicely centered at 0, it looks pretty random. Looks like there's really not much pattern left. So this is a good thing. But that particular plot isn't helping me to see if there is a seasonal pattern. And in fact, one way we could do that is by labeling those points with the months. Here's the code to do that. So now we've plotted the difference of the series, but we've added the letter associated with the month. Do you see any problems here? Well, we see the seasonality. It starts to pop out now once we've put those plotting symbols on the data. So you'll notice Septembers, Octobers, and Novembers, these are mostly at the low points. And December, that's mostly at the high point. Let's check out a time series of the seasonal difference of the first difference of the log series. So now with seasonal difference, I'm not just taking the difference between the point right next to me, I'm taking the difference of the point that's 12 steps away from me, right? So I want to subtract January's value with last year's January value, and that's going to eliminate the effect of the season. Here's the code to do that in R, and here's the corresponding output. Notice now, we no longer see that up and down pattern, and very few of those months are clustering toward the top or the bottom of the graph. Now, we chose to do the plot of seasonal plotting symbols, and the seasonality is much less obvious now. In fact, some of those Decembers are high, some of them are low, some of the Octobers are high, some of them are low. And so we've accounted for the structure in our data by taking the log, taking the first difference, and then taking the first seasonal difference. So one question we might want to ask is, well, how much is this time series correlated with itself? And we get that from the sample autocorrelation function. Here, the ACF, or the autocorrelation function, gives us the correlations between the series, y sub t, and lagged values of the series. So with time 1, time 2, and time 3 behind it. This is basically a visual plot of your autocorrelation, those row 1s and row 2s that we defined earlier. Now, the ACF can be used to identify any possible structure in the time series data. And this can be kind of tricky since often there isn't a single clear-cut interpretation of the sample autocorrelation function. But the ACF also models the residuals. So the idea for an autocorrelation function of residuals is that there shouldn't be any significant correlations, right, at any lag. Because then your model has taken into account all of the structure in the data. So the goal when you do ACFs for residuals, after you fit your model and you look at what's left over, is to not see any kind of correlation, right? Because you've already accounted for all of that. And if you do see correlation, it influences then what you do next to the model. All right, here's the ACF of the residuals for the wages example, where we used an Ar1 model. The lag, which is the time span between observations, is shown on the horizontal line, and the autocorrelation is on the vertical line. And those blue lines you see, those are the bounds for statistical significance. So values that are below the blue line are great. That's considered like noise, just stationarity. And once we're above that, that means that at that lag, the autocorrelation is significant. All right, so notice in wages, at a lag of 1 and 2 and 3 and 4, even 5 a little bit, we've got some correlation. And you'll also notice here that some of those values, after you go out beyond 5, fall between the blue bands, so they're not significant. So we've got structure in the data that we somehow need to account for. Now, in general, a partial autocorrelation is a conditional correlation. This is the correlation between 2 points of a series under the assumption that we take into account values that are between those 2 points. So, for example, suppose I want to get the partial autocorrelation of y sub t with, say, y sub t minus 5. What I would do is take out the effect of those y's that are in between them so that I only get the effect of those two on each other, not their conditional effect of the values in between. So the partial autocorrelation function gives us that information. And it's really significant here because notice, for the wages example, there's significance at lag 1, and most of the rest of them are not significant. So this hints to us what our model should be. In fact, for this particular case, this would say that it's an Ar1 model. So we find Ar1 models by looking at the PACF and seeing what lags are significant. But you'll also notice, check out what happens at lag 13. Notice that there's also some significance there. And that's where the seasonality is popping out. Now here's the ACF of the seasonal difference of the first difference of the logged series for air passengers. This was that data that we showed was normal, the residuals, right? What does that ACF look like? Here we have the autocorrelation function for the first and seasonal difference of the log of our airline passenger data. Now you'll notice here, there's a significant ACF at a lag of 1 and a lag of 12. and a slightly significant one at a lag of 3, although it's not as prominent. Now we can also look at the partial autocorrelation function. Again, the PACF, or partial autocorrelation function, gives us influence for an autoregressive component. Whereas the ACF, what we just looked at, the autocorrelation function, gives us the influence of the MA component. Now notice here, you don't even see the blue lines on this partial autocorrelation function. And that's because none of the lags are significant. So now we want to model this data. And based on the ACF and the PACF, we would model it using a moving average. So remember, we had significance at a lag of 1 and a lag of 12 at the ACF. So that indicates a moving average process. Y sub t equals E sub t plus theta 1 E sub t minus 1 plus theta 2 E sub t minus 12. So that E sub t minus 1 is the lag of 1, and the E sub t minus 12 incorporates that seasonal lag at 12. Here's the output that we get from R. So we got to estimate that theta 1 and that theta 2, and R does that automatically for you. For our model, we're going to use the ARIMA function, and we're applying ARIMA to the log of our data. Notice it gives us the coefficients. So MA1 has a coefficient of minus 0.4018, and you see the associated standard error. And that SMA, that's the seasonal coefficient for the MA12 model, which gives us a value of negative 0.5569. So now that we've fit the data, we'd like to be able to use our model to make predictions or forecast. Let's produce the forecast for this series with a lead time of 2 years. All right, check out the plot here. So this is of the log of our data. You see that nice seasonal pattern, and look at those last 12 points. We've predicted the series 2 years out. Now, the forecasts follow the seasonal and the upward trend of the time series very nicely. And those forecast limits that you see, they provide us with a clear measure of the uncertainty in our forecast. Now, we can also plot that back into the original terms of the data, as you see here. Now, in the original terms, it's easier to see that the forecast limits actually spread out as we get further into the future. So this leads us to the pitfall of time series data. The short-term trend is not the same as the long-term trend. And so what looks like a line in the short term might actually curve over a longer time period. So just because we find one kind of seasonality in a time series, it doesn't mean that there's not a second or a third kind as well. Just think of the cycles of days versus weeks versus years. And any time series of, say, currency in dollars or pounds, it has to take into account the fact that the value of money changes over time. So if we were modeling, say, changes in home prices over time, then we would need to correct our data to some common base. Now, usually we correct by starting with a base year, often as the start or the end of our series or the current year. And then we adjust the values based on changes to some official inflation statistic, like the Consumer Price Index. Well, in any case, perhaps the biggest advantage of using time series is that we can use a model of the past to better understand the future.